All right, so building off of our discussion last time, where we put together a formulaic representation of the radius of convergence of a power series for any power series at that. Let's put this notion into context. So let's work through an actual example related to this. So here is a power series. It's the sum from n equals 0 to infinity of n times x plus 4 to the n over 3 to the n. We're going to determine a few things. We want to determine the center of this power series. We want to determine the radius of convergence of this power series. We want to determine the open interval of convergence for this power series. Okay, first off, the center. That's not too difficult because the center is just going to be the value for x that wipes away all of these terms of degree 1 and higher, and the value for x for which that's true would be x equals minus 4, right? So the center is just x equals minus 4. That's nothing too wild or crazy. Now, when it comes to radius of convergence, we need to use this formula in order to determine the radius of convergence. So the radius of convergence is going to be a limit as n goes to infinity of Cn over Cn plus 1, absolute valued. Well, in order to determine this expression, we're going to have to figure out exactly what Cn is. Now remember, Cn is just the general form of the coefficient of your power series, and maybe the cheapest way to see this is just to take that power of x plus 4 and write it out in front so that you're just looking at the coefficient straight away. So here's the general form of your coefficient, here's your Cn right there. So in other words, Cn is just n over 3 to the n. So with that, we can now compute the radius of convergence, because the radius of convergence should be the limit as n goes to infinity of Cn over Cn plus 1. So to compute the radius of convergence, we just use our radius of convergence formula. And what do we get? Well, upstairs we get Cn, which is n over 3 to the n. Downstairs, we get Cn plus 1, which is n plus 1 over 3 to the n plus 1. Now, you might be thinking, Professor, isn't this backwards of how the ratio test works? The ratio test has the n plus 1th term over the nth term. Yes, it is the reciprocal of the standard way we think about the ratio test, because when we were solving the inequality above related to radius of convergence, remember, we needed to divide away by our standard ratio test limit. So in order to divide away by that, well, we're going to have to divide a fraction which is multiplied by its reciprocal, and hell, that's why we get that fraction in the inverted form from how it normally looks with respect to the ratio test. Nonetheless, the skills which we've acquired when working with ratio test limits can apply here, because in fact we can just keep, change, flip, and get ourselves the double-decker fraction simplified. And if we take a moment to organize, we could take our n and our n plus 1 and write them over one another. We could take our 3 to the n plus 1 over our 3 to the n and write them one over the other. When you take the limit of this guy, this is just going to be a degree 1 over degree 1 equal heavy rational expression. That's going to have a limit of 1. And then whenever you work this guy out, let's see, all of the powers of 3 downstairs are going to cancel, leaving 1. And in fact, just 1 power of 3 remains above. So whenever you look at this expression inside the limit and run the computation, you get 1 times 3 over 1. Well, 1 times 3 is just 3, and ultimately then 3 is the radius of convergence for this series. Okay, so now what does that mean? Thinking about this series in terms of its interval of convergence, we know the center of the interval of convergence is minus 4. And we know the radius is 3, which means 3 units on either side of minus 4, this series will converge. So what is 3 units on the right of minus 4? I believe that is minus 1, correct? And what is 3 units on the left of minus 4? Well, 3 units to the left of minus 4 will be minus 7. And so to compute the open interval of convergence, we do precisely what was just described. We say from minus 4, we're going to go 3 units to the left and subtract 3. We're going to go 3 units to the right and add 3, because that is the radius within which our power series converges. So run all of the numbers together. We get an open interval of convergence of minus 7 comma minus 1. What does that mean? That means if you take any number between -7 and -1 and plug it into this series for x, plug in x equals -4, plug in x equals -2, plug in x equals -4, -6, -6.2, -1.3. Plug in any number that's on this open interval, and your power series here is going to converge, because what we deduced was that this expression here, the limit of Cn over Cn plus 1, corresponds to the radius of convergence via the ratio test. So ultimately, by the ratio test, we know that any value between -7 and -1 is going to converge, or is going to result in a convergent series when we plug that value in for x. So these are values where our series will converge, and in fact, outside of this interval, if you go beyond the boundary of the interval, these will be values where the ratio test would give you an expression greater than 1, where the ratio test would diverge. But the long story short here is we have an open interval of convergence of -7, -1. How did we get that? We identified the center. We used our formula for the radius of convergence, and then we just used that notion of radius of convergence to go 3 units to the right by adding 3, and 3 units to the left by subtracting 3. It's that simple to get your open interval of convergence once you know the center and once you know the radius. Okay, having gone through this example and having worked out all of the information that we did, I just want to add one additional note. Sometimes you know that limits going to infinity have values that evaluate to infinity. That is possible. So it is quite possible that the value of this limit is infinite. Should the value of this limit be infinite, think about what that would mean. That would mean that you should be able to go infinitely many units to the right and infinitely many units to the left of the center of your interval. And well, think about what that would mean. That would mean go infinitely far to the right. How far do you go? That's all the way down the number line. Go infinitely far to the left. How far is that? That's all the way down the number line in the other direction. So if you take your center and add infinity and take your center and subtract infinity, you will get the interval -infinity to infinity, which is in fact the entire number line. And so should you end up with a series whose radius of convergence computes out to be infinity, nothing to worry about. That's a perfectly fine thing. What that means is that you have a series for which any x value yields a convergent series, which is pretty cool when you think about it, in fact. And that's just what you need to deal with if you ever get a radius that is infinite. Should, on the other hand, you get a radius that's finite, like say, this radius instead of being 3 was 13, well then we just add 13 units to the right and take away 13 units to go to the left, and then we get ourselves a corresponding interval of convergence. So hopefully through this example you can see that computing radius of convergence and open interval of convergence are really not that wild or crazy. To compute the radius of convergence, we do need to have this formula in mind, because without this formula, computing the radius of convergence is a messy application of the ratio test every time. And to get the open interval of convergence, once you have the radius, it's really not that bad either, right? Just go from the center, the radius units to the right, and the radius units to the left, and you'll get yourself an interval. And that interval is precisely the open interval on which your power series will converge, thanks to the ratio test.